So in the last session, we did the Newton's law, like Newton first, second, and third law of the motion. So today we'll discuss some examples, the practical questions related to Newton's law. So according to Newton's first law, if an object is at rest, it remains at rest, or if an object is moving at a constant speed, it will continue to move at a constant speed until an unbalanced force acts on it. That's the Newton's first law. And according to Newton's second law, the resultant force which is acting on the object will cause an acceleration, and acceleration is proportional to the magnitude of the resultant force. That was a Newton's second law. Newton's third law, action and reaction forces are equal but opposite in directions. So that is the Newton's third law. Now, free body force diagram. What is a free body force diagram? Actually, the free body force diagram represents all the forces which are acting on the object. The arrows shows like the direction of the force is represented by the arrow, and the length of an arrow shows the magnitude of the force. If you draw longer arrows, it means it has a greater magnitude. For example, if object is on inclined surface, or let's take an object is there placed on the surface, and we want to, and it is stationary. If this object is stationary or object is at rest, and we want to draw a free body force diagram for this object. So free body force diagram represent all the forces which are acting on the object. So what are the forces acting on this object? First thing, the weight of this object which is acting downward. Then there is a normal contact force because it is in contact with the surface that is pointing upward. We can represent the normal contact force by letter N, or you can also use the letter R. So both ways it is, because it's a reaction force, you can use R, or a normal contact force, you can use the letter N. Because this object is stationary and it is not acted upon any force which is horizontal, that's why we did not draw. And because this object was stationary, so if we draw, like example, if the normal contact force, we draw 2 centimeter arrow, and the weight should also be 2 centimeter. Why? Because it shows that the magnitude of the two forces are equal. The length of the arrow shows the magnitude. If you draw a free body force diagram and you drew weight, the length of the arrow which is representing a weight is longer than the normal contact force, it means there is a resultant force downward. So the size or the length of the arrow is also important whenever you draw a free body force diagram. Same way, if an object is moving so if an object is stationary or at rest, if this object is not moving or object is stationary, then in a free body force diagram, the length of the arrow should be equal and they cancel out each other. Same way, if we have an object which is floating on the surface of the fluid, and we want to represent the free body force diagram because this object is stationary at rest. So I want to draw the free body force diagram. How to represent the free body force diagram? The weight of this object is acting downward, and there's another force, the fluid will apply, and what we call that as upthrust. So two forces which will act, one is the upthrust and the other one is a weight. Because this object is stationary, so the length of the arrow which represent the upthrust should be equals to the length of arrow which represent the weight. And what if the object was moving through the fluid with a constant speed? So there's an object which is moving through the fluid at a constant speed. This object is going down, but it has a constant speed. So if an object is having a constant speed, again, when constant speed or stationary, the resultant force is zero. First, what are the forces which are acting? The weight is acting downward, so we know W. Then there are two upward forces. How to represent those upward forces? I can represent them separately. Example, the length of the weight I represented by 2 centimeter. So the two upward arrows which I will draw, one will be the upthrust. I will draw 1 centimeter, and another one is a drag force or a viscous drag. The drag force or a viscous drag, it's a force of the liquid to oppose the motion. Liquid have a tendency, liquids and gases, they have a tendency to oppose the motion, and we call that as a drag force or a viscous drag. So if I draw 1 centimeter for the upthrust, I will draw 1 centimeter for the viscous drag. Why? Because the resultant force, I want the resultant force to be zero. So if we don't want a resultant force, it means the length of the arrows we are drawing upward and the downward should be equal. Or there's also another way to do this question, like free body force diagram. You can represent the upthrust and the drag together. How you can represent the upthrust and the drag together? So you can draw two arrows on the same line. One is representing upthrust, another is representing the drag, and the weight is acting downward. The length of this, the total sum of this drag plus upthrust should be equals to weight. Is it clear? Any doubt in this till now?
No, sir.
But what if the object was accelerating? Let's take the same example. The object is moving through the fluid and this object is accelerating. So a container filled with a fluid and the object is accelerating downward. If it is accelerating downward, it means the downward force should be greater. Accelerating downward, or we say decelerating upward, is having the same meaning. The difference between the two is, like here, when we say it is accelerating downward, so the direction of the motion and the direction of acceleration both are same. But when we say it is accelerating upward or decelerating upward, what does it mean? It also means that the direction of the motion and the direction of acceleration is opposite. Direction of the resultant force. So it both have the same meaning. When we say the object is accelerating downward, it means the direction of the motion and the direction of acceleration is same. But when we say the object is moving up, but it is decelerating, it means the direction of the acceleration is opposite to direction of motion. Now, if this object is accelerating downward, it means the downward force should be greater. So what are the downward forces acting? The weight is acting downward, the upthrust is acting upward, and the drag force is also acting upward. Let's first take a simple example that this object is accelerating downward. So if this object is accelerating downward, it means the downward force should be greater than the upward force. So when we draw the free body force diagram, in that case, the upward arrows should be shorter than the downward arrows because the resultant force is downward. So W, this will be the upthrust and the viscous drag or a drag force. So the size of the arrow in a free body force diagram, the size of the arrow is important. That if the two forces are equal in magnitude or the resultant force is zero, then we draw the same length. But if the one of the force is greater than the other, then the one which is having a greater magnitude, you should draw it longer. And if I want to write the equation for these explaining the motion, like in this case, the object was stationary. So when object is stationary, the resultant force is 0. So I can say weight minus the upthrust should be equal to 0. Because the result of the two forces when object is stationary or it moves at a constant speed, the result should be 0. In this case, it is also moving at a constant speed, so weight is acting downward minus the upthrust minus the viscous drag, and what should be the result? The result should be 0. Why the result is 0? Because the object is moving at a constant speed. So whenever the constant speed or object is at rest, according to Newton's first law, the resultant force must be 0. But what about the equation for the third example? As this object is accelerating downward, so which is a greater force? Weight is greater. So we can say weight minus the upthrust minus the viscous drag or the drag force should be equals to ma. Why we wrote ma? Because according to the Newton's second law, that the resultant force is always equals to the product of mass times acceleration. Is it clear now? The equation for this motion?
Yes,
Anyone
sir.
having a doubt?
Mm.
So if an object is at rest or it moves at a constant speed, in that case, we will consider no resultant force. But what if the object is accelerating? So an object is accelerating, then we have to take a resultant force should be equals to ma. So another example, say if the acceleration opposite to the direction of the motion, we call deceleration. Yeah. If the direction of the acceleration is opposite to the direction of the motion, we call deceleration. Another example, say this container is filled with a fluid and we have an air bubble, and this air bubble is accelerating upward, and the direction of the motion is also up. And I draw the vectors, I do the weight, I do the upthrust, and I do the viscous drag. Can you identify the mistake in this diagram? Can you identify two mistakes like in this diagram? Two mistakes in this diagram. Yeah, one of the mistake, as some of the student mentioned, that the length of the arrow, like because the object is accelerating, so I cannot draw the same length of the arrows upward and downward. That is one of the mistake. What about the second mistake in this diagram? Yeah, the length of the weight should be less. That's the same thing. Like one of the mistake that students mentioned, that upthrust and the drag which I drew should be more than the weight. That is one of the mistake that pointed out. What about the second mistake in this diagram? That's good. The drag should be opposite. The direction of the drag, because the object is going up. So if object is going up, drag force always oppose the motion. Here the direction of the drag is same as the direction of the motion. So when I drew the arrow to represent the drag, so I should represent that the weight and the drag force are acting downward and the upthrust is acting upward. And because this object is accelerating upward, when object accelerate upward, how to write the equation? So upthrust is greater. So upthrust minus the weight minus the drag is equals to 0. Is it correct? Upthrust minus weight minus drag is equals to 0. Is it correct? Yes or no? So why it is not correct? Because there is a resultant force. The system is accelerating. Whenever object accelerate, the resultant force should be equals to ma, mass times acceleration. Is it clear, this example? Anyone having a doubt or a question till this point?
No, sir.
Now, about the inclined surface, example, we have a horizontal surface and object is placed on the inclined surface. So object is placed on the inclined surface, and we'll take different examples. Say first example, the object is at rest. And we want to draw the free body force diagram of this object. So how we can draw the free body force diagram? So first thing, the forces which are acting, the weight of this object is acting downward. So weight of this object is acting downward. That's one of the force. The second force is a normal contact force. And which is perpendicular to the surface. That's right. What about the third force? Because the object, the natural tendency when you place an object on the inclined surface, the natural tendency of this object is to slide down. So means there must be another force, or the force of the friction, which is acting opposite to oppose the motion. So naturally, because of the component of the weight, so this is the weight of an object. This one is representing the friction, and this one is representing the normal contact force. You can write letter N or you can write R. Both ways it is correct. So R you write or N you write, both ways it is fine. Now, when object is stationary and we have like 3 or more forces are there, now how to know that whether the object is stationary from the length of the arrow? So when you complete a triangle, by combining these forces, it should make a complete figure, like a closed figure. So if I draw weight here, then I drew the friction, and then I draw the normal contact force. So if we reach our starting point back again in a forced triangle, this is also called a forced triangle. So in a forced triangle, if our starting position and the final positions are same, it means what is the resultant force on the object? It means the resultant force on the object is 0. So in this case, the resultant force on the object is 0. And if the resultant force on the object is 0, it means the object can either be at rest if it was a stationary object, or if it was a moving object, it will continue to move at a constant speed. So sometime you have 3 or more forces, so you join them according to their lengths. And if your final position, starting position and the final positions are same, it means that the resultant force on the object is 0. This is also another way of identifying the resultant force on the object. If what if it was not forming a closed triangle, like when we complete this and it was not able to complete, like forming a closed triangle, it means there must be a resultant force. Now, what is important part on a inclined surface is a resolution of the vector. Resolution of vector means like we break down the vector into the component. So example, on the inclined surface, it is making an angle theta. So when we resolve this inclined surface into the component, we draw the horizontal line, the dotted line, and we drew the vertical line according to inclined surface. So the angle here, the angle between the horizontal surface and the inclined surface is always same as the angle between the axis which we took and the weight. This is always fixed. Mathematically, it can be shown, but as we are not going in detail of the derivation of how the two angles are same, so we'll just consider always whenever object is making certain angle with the inclined surface, that angle will be same as the angle between the weight and the axis which we took. So if this angle is 30 degrees, what will be this angle? It will be 30. If this angle is 50, what will the angle here? 50. So the angle between the inclined surface and the horizontal surface is always same as the angle between the axis which we draw on the inclined surface and the weight. Now this weight will have the two components. One of the component is with an angle, this component. What we'll write? Cosine or sine? The component of the weight which is with an angle, sine or cosine on the inclined surface.
Cosine.
So component which is with an angle, so this will be W cosine theta. And there will be a component of the weight which is opposite to the angle. So when we drew a component of the weight which is opposite to the angle, what will be this component? So this component will be W sine theta. So W cosine theta and W sine theta are the two components which are components of the weight. Now for this example, if you want to write an equation for object is stationary. If an object is stationary, the resultant force should be 0. So first, as you can see, R is acting upward, and what is balancing the R? Which component of the weight is balancing the R? W cosine or W sine?
W cosine.
So W cosine is balancing the R. So we can say that R minus W cosine theta is equals to MA. What is the mistake here?
It's equal to 0.
It's equal to 0 because why it is equals to 0? As this object is stationary or at rest and it is not accelerating in the plane. So R minus W cosine theta is equals to 0, or I can also say R is equals to W cosine theta. What about the second component? As you can see, the W sine theta is there. This is a component W sine theta pointing towards the base, and friction is there which is opposite. So we can say that any one of them, because both forces must be equal as the object is not accelerating. So W sine theta minus F is equals to 0, or I can say W sine theta is equals to F. So whenever object is on inclined surface, and when object is on inclined surface, or if it is at rest, or maybe it was moving at a constant speed, so in that case, the R will be equals to W cosine theta and F will be equals to W sine theta. Is it clear? Anyone having a doubt or a question about the resolution? And
No, sir.
so weight, what we did here, we resolved the weight into the component. Like this was a weight. So we break down the weight into the components into parts. So one of the component of the weight is W cosine theta, and one of the component of the weight is W sine theta. So weight is actually break down into its component. So one of the component, the W sine theta, balances the friction, and W cosine theta balances the normal contact force. And because this object was stationary, that's why, or if it was moving at a constant speed, both cases, the object, the two components of the weights will balance out their opposite forces. But what if this object was accelerating downward? An object is there on the inclined surface and it was making an angle theta. So the components which are acting means the forces which are acting, the weight is there, the friction is there, and the normal contact. And in this example, the object is accelerating downward. Okay, like it is sliding downward or accelerating downward. Now, first thing, whenever you see a question related to inclined surface, you will always resolve the weight into the components. So we'll take the axis here. We'll take the axis. The normal contact force should always be 90 degree or perpendicular. So this is a normal contact force. R is there, friction is there, and this is the weight. We resolve the weight into the components. Here it is making an angle theta. So weight will have two components. The one is with an angle. So this will be W cosine theta, which is pointing downward. And another one will be the W sine theta opposite to the angle. So when I want to write the equation, in this example, the object is accelerating in this plane. So when it is accelerating along the inclined surface, so we can say that W sine theta should be greater. So W sine theta minus the friction equals to MA. So W sine theta minus friction is equals to MA. This is the equation. If I say the friction is very small, if the friction is very small, we can neglect the friction. So if we neglect the friction, I can also say that W sine theta is equals to MA. W is equals to mg. You have studied that formula, that weight is mass times the gravity. So in place of weight, I can write mg. So mg sine theta is equals to ma. M is common both sides, so I can cancel out. So if m cancel out with another m, what I can say that g sine theta is equals to a. So means if I need the acceleration on the inclined surface in which we ignore the friction, like the friction is negligible, on inclined surface, A is not equals to G. A is not equals to G on inclined surface. For objects which are falling, A is equals to G without air resistance. But objects which are moving on the inclined surface without a force of the engine, like there should be no engine, nothing should be there, only the object, because of their weight, they are sliding downward. In that case, the acceleration of those objects on the inclined surface is equals to G sine theta. And this formula is derived on the base that the friction is negligible. We neglected the friction. And in this case also, there is no air resistance here. We ignore the air resistance. So ignoring the air resistance, ignoring the frictional force, when we compare all, like any kind of friction is zero, air resistance, drag, or friction of the surface, all are zero. In that case, we can ignore this friction and we can say W sine theta is MA, and M, when we simplify this, so mg sine theta is equals to MA, M will cancel with M, so A is equals to G sine theta. That acceleration is equals to G sine theta. So on inclined surface, without a friction, if an object slide down because of its weight or the component of the weight, then acceleration is always G sine theta. Is it clear about the acceleration?
Yes.
What about the component with, so R and W cosine theta, there is no acceleration in a vertical plane. Like in this plane, vertical plane, it does not accelerate. So if it does not accelerate in the vertical plane, so we can say R minus W cosine theta is equals to 0. Because in the vertical plane, there is no acceleration, or we can also say R is equals to W cosine theta. So R equals W cosine theta, that remains same, but the along the inclined surface, because it was accelerating, that's why we wrote W sine theta minus F was equals to MA. So this motion in this plane, it was accelerating, but in a vertical plane, the acceleration was 0. Like if normal contact force was greater, then this should go up. If the weight was greater, then it should move down, like W cosine theta. But both are balanced, that's why it moved along the surface, but it was accelerating towards the end. It shows that the component of the weight, which is W sine theta, is more than the friction. That's why it was accelerating. Is this clear on inclined surface? Anyone having a doubt or a question? The formula? Now, example, a boy is pulling a box, a heavy box, and we want to show the free body force diagram. So example, if you want to draw the free body force diagram for the box, so what are the forces which are acting on the box? The weight of the box is acting downward. The normal contact force is acting upward. You can write N or you can write R. The man pulls the box, so the force of the pull of the man on the box, and this because it is in contact with the surface, the friction is there. So these are the free body force diagram on the box. But if you want to represent the free body force diagram, we want to represent the free body force diagram for the men. So what will happen? First thing, because according to Newton pair forces, if man is applying a force of say 30 Newton on a box, the box will also apply a same force but in opposite direction. So the box will also apply a force of 30 Newton on the man. That's why the pull of the box is shown here. Then the weight of the man is acting downward. As you can see, the weight is acting downward. He is in contact with the surface. So there will be a normal contact force acting. So the normal contact force is also given. But what about the friction? The direction of the friction. You see the direction of the friction is towards right. Why the direction of the friction is towards right? Because just try to imagine if you try to pull the box, which direction you try to push your leg, feet. If you want to pull anything in this way, which direction you tend to push your feet? Which direction you tend to push your feet? So you tend to push your feet in the left hand side. That is where you want to push. So when you tend to push your feet on the left hand side, what is the direction of the friction? The direction of the friction according to the leg, according to the feet, it will be towards the right hand side. Because the friction always opposes the motion. Same way, if the tires, say a car is, the tires are rolling and it is moving in this direction. That's the direction of the motion. What will be the direction of the friction? What will the direction of the friction? Right or left? What will be the direction of the friction?
Left.
Everyone answered till now left, but the correct answer, the direction of the friction is towards the right hand side. How? As I mentioned, friction always opposes the motion. What you're considering the full motion of an object. But when you consider the motion, you consider the motion of the surface. As you can see, these tires are moving in this way, the tire rotation. So the rotation of the tire is in this way, the clockwise. So to oppose the motion of the rotation of the tire, what will the direction of the friction? The direction of the friction will be forward towards the right hand side. So when we say the friction always opposes the direction of the motion, it does not mean the total net direction of the motion. It means the friction opposes the direction of the motion of the surfaces. If the box was moving towards right, the direction of the friction is towards left. If the tire is rolling, I'm not talking about the motion of the object, whole object. When the tires are rolling, if the tires are rolling in this way, because it is moving in this way, what should be the direction of the friction? The direction of the friction should be forward. Is it clear, this one? This example about the friction? So
Yes,
for a
sir.
friction, you don't consider the whole object, you consider the surfaces which are in contact. So the contact surface was moving in opposite direction. So like if it was rotating clockwise, the friction will be opposite to that. So if friction depends on the surface, not the overall motion of an object. So when a car moves, actually the friction of the tires in the track decide the speed at which the car moves. Because what will happen, say, so example, the engine rotate, like the chemical energy convert into kinetic energy, and it rotate the wheel in this direction. So when it rotate the wheel in this direction, so what will happen? There will be a friction between the track and the tires. So as a result of that friction, what will happen? The friction try to oppose the motion. So the direction of the friction will be in this way. So greater the friction between the track and the tire, it means the car will have a better grip, and greater friction means it will have a greater forward force and it will accelerate forward. So the engine convert the chemical to kinetic and which rotate the wheels. When it rotate the wheel, the movement of the car is not due to the rotation of the wheels, is because of the friction which oppose the motion, and that friction is forward. That's why the net it produces a net resultant force, so the car can accelerate. Is it clear? This one? Anyone having a doubt or a question till this point?